Welcome. In this video, we're going to begin talking about some more trig identities, specifically the Pythagorean identities. So before we get going, let's just think about some trig identities we already know. We have these basic identities. So we know that sine is reciprocal to cosecant and vice versa. Cosine is reciprocal to secant, and tangent is reciprocal to cotangent. We also know that tangent can be written as sine over cosine and vice versa. Its reciprocal function, cotangent, is cosine over sine. We know that odd functions have rotational symmetry about the origin. So sine and tangent are both odd functions, which means sine of negative x is the same as negative sine of positive argument x. Whereas cosine is even, and it has reflective symmetry across the y-axis. And we can say cosine of negative x. Essentially, we can just take that negative and throw it away and make it cosine x. So we know these, we understand them, we have them stored. Now we're going to talk about some other identities. So our Pythagorean identities. And we'll derive it, but I find it helpful to write the identities first. So we have three versions of the Pythagorean identity, and really we just know one, and then we can form all of the others. So I know that sine squared theta plus cosine squared theta is equal to 1. You're saying, well, Ms. Stein, how did you know that? I'm going to show you in a second, but we're just going to list this out. So this is our main Pythagorean identity. Addition's commutative, so it's the same to write cosine squared plus sine squared theta, right? That's sine squared theta plus cosine squared theta equals 1. Now, if I took sine squared and I divided all of these terms by sine squared divided by sine squared, well, sine squared over sine squared would give us 1. What would cosine over sine give us? Cosine squared over sine squared. That would create cotangent squared theta. And similarly, if I take this 1 and divide it by sine squared, that will give me cosecant squared theta. All right, and I can do this one more time. I could take all of these terms and divide them by cosine squared. So sine squared divided by cosine squared is tangent squared theta. Cosine squared divided by cosine squared would be 1, and 1 divided by cosine squared would be secant squared theta. So essentially, I have 3 Pythagorean identities. And what I'm showing you here is I just memorize this one, and then I know I can divide all of the terms by sine to get this second identity, and divide all of the terms by cosine to get the third identity. And these identities, they're not going to always appear in this order. So all 3 of these identities can be rearranged into several equivalent forms. So that first Pythagorean identity, sine squared plus cosine squared equals 1. That could also be written as sine squared theta equals 1 minus cosine squared theta, or also cosine squared theta equals 1 minus sine squared theta. So that was just using the additive property of equality to rearrange those. Same with the next one. I could say that 1 equals cosecant squared theta minus cotangent squared theta, or also cotangent squared theta equals cosecant squared theta minus 1. And lastly, with my tangent identity, I could say that tangent squared theta is secant squared theta minus 1, or rather 1 equals secant squared theta minus tangent squared theta. All right, so the point of this is, and I'm going to show you how we can derive this from what we know about right triangle trig, is that we really only need to store this one identity. Again, we divide everything by sine to get this one in orange, and the third one here in purple, we divide everything by cosine. And with a little bit of rearranging, just using algebra, I have 6 other versions of these identities. All right, so again, know this first one, derive the other 8 as needed. Be familiar enough with them that you're like, hey, that might be an identity when I see it, and then it's pretty quick and easy to write these down. So in case you're wondering how this sine identity, the sine Pythagorean identity is formed, let's derive it. Now, at this point, you have heard me say the word derive several times. Derive. What does it mean to derive something? Well, in order to derive it, that means we're going to take something that we already know and assume to be true. We use it as though it's true, and then we're going to apply rules and laws that we also know are working or that they work and are true, and develop, derive, create a new identity. So here we're going to derive Pythagorean identity. And as I'm sure you're guessing, we're going to start this derivation with the Pythagorean theorem. So I have some angle theta, some acute angle theta in a right triangle, and I'm going to list my sides. I have my hypotenuse, which we are starting to call r instead of h, but any variable works. And then a horizontal side, I'll call that x, and a vertical side, I'll call that y. So setting this up, let's start with the Pythagorean theorem, which is x squared plus y squared equals r squared. And again, these variables, they can be whatever we want them to be. I'm just trying to use variables that we've seen already. So I used x for the horizontal, y for the vertical, r for the radius or the hypotenuse. So let's think about developing some trig identities. Now, if we're considering theta, how does x relate in our SOHCAHTOA language to theta? And x is touching theta or adjacent to theta, whereas y is opposite theta. And then, of course, my r there, that represents my hypotenuse. So if we wanted to translate this into some trig identities, what could I do? Well, I could write that cosine theta would equal x over r. I could also write that sine theta equals y over r. And because we know right triangle trig, we know that these ratios are the correct statements. So I'm going to take this Pythagorean theorem and I'm going to turn it into something with sines and cosines. Pretty quickly, I see I need a ratio. So what I might do first would divide all of these terms by r squared. So what does that give me? That gives me x over r squared plus y over r squared, and r squared over r squared is positive 1. Now, it should be easy for us to see that x over r is equal to cosine theta, and y over r is going to be equal to sine theta. So this is the same as writing cosine theta squared plus sine theta squared equals 1. Therefore, cosine squared theta plus sine squared theta equals 1. And that's our Pythagorean identity. So it's pretty easy to develop using right triangle trig and the Pythagorean theorem. And of course, cosine squared plus sine squared theta, that's equivalent to sine squared plus cosine squared by the commutative property of addition.